Like, I love how you were like, yeah, I can hear you. All right, here we go. So if there's any quick questions, I can help. I'm going to try to move the question period to the help session. So we only got through one topic yesterday, and I don't want to fall behind in the curriculum because there's some pretty cool things later in this course that I want you to at least hear about, so that when you study if you go on and you study the details of it, you'll understand the main concept you're actually studying rather than just focus on equations and whatnot. They're pretty cool ideas. Anyway, so are we any quick questions before we get going? No? All right. Let me just do a quick check here. Got Kira. Kira, did you get my email?
Probably. I haven't checked that in a couple days.
You need to be checking your school email regularly when you're doing online or virtual courses. I need you to respond to the email I sent you. Okay.
All right.
Thank you. So on the 20th, I've got Kira and G. I'm just gonna go last names because it's alphabetical for me. Holiday, Kayla, Horn, Page, and so David's just probably not going to log in because he's doing that thing instead. Sarah as well. All right. Margot. Is Margot part of that math thing page?
No, I don't know. She's not.
Okay. All right. So it looks like I'll probably end up marking you as present page, even like because our attendance policies are strange. Rita or in this board or whatever. It's like if I see you for 5 minutes, you're counted as present. So if you're wondering about attendance records. Anyways, here we go. So screen sharing, recording, we're good to go. So we're going to actually develop an equation for centripetal acceleration and forces and so on in this lesson. And I just want to make sure you are aware. You might have noticed that there wasn't a ton of practice questions to do with free body diagrams like these ones. Not those ones there, but the water bucket. You know, this kind of stuff where you've got, oh, I have to remember that whether the tension force is up or down and whether the centripetal force is up or down and that. So in this case, in the bottom case, we're putting in the net force as an upwards force. The centripetal force is the net force. It's an upwards force at the bottom of the circle. At the top of the circle, it gets put in as a minus, you know, like it's if you know the value of it, which is often the case because we're going to be developing an equation for it today. So you wouldn't have had, there wasn't really many questions, any questions maybe in the textbook where it says like, just draw the free body diagram for these different situations. You're going to be drawing those free body diagrams in the context of actually calculating numbers in tonight's homework. So you might need to refer to these pages or the page that was dedicated to it over here, where it's like this one in particular, I guess, where we have vertical uniform circular motion and the idea of what direction these things are in, right? So in position 2, for example, I'm showing here, you know, that there's a positive right there, positive net force, positive centripetal force. And in the case 1, you can see there was a negative centripetal force put in. So that's critical for the questions you're going to do with the new equations, or new in quotes because I've already sort of told you them in the past. Anyway, so we're going to actually see why they're true. So y is mv squared over r equal to the centripetal force is the idea. All right, so basically we're going to come back and reveal the answer for this once we've developed it, or I could just show it and then confirm it or whatever. But so we want to develop an equation for acceleration first, because that's simpler than developing an equation for force. So acceleration we definitely have to just go back to our basics and remember that acceleration is, what do we know about acceleration? Acceleration fundamentally is, someone knows, change in what divided by change in what. We're not talking about special stuff to do with circular motion. We're just saying acceleration is delta something over delta something. Everybody's microphone's broken today. Really? Acceleration.
Is one of them delta V?
Yeah, delta V over. It's the change in velocity per
Change in
unit.
velocity over time.
Yeah,
Change in time.
delta V over delta T. That's just the basics we're starting with. So I did want to make sure everybody has a chance to like be forced to think about that and realize the simplicity of what we're starting with here. It's well-known stuff. Okay. So we can solve, or also we know that delta V equals V2 minus V1, of course, right? The idea of a tail-to-tail vector subtraction is related to that in this question, just like we looked at yesterday, right? So if I'm putting V1 and V2 tail to tail, and I'll even add in here that we have final minus initial concept to help keep track of which ends which for our delta V. So V2 on here must be this one, so that's my final. This is my initial, and so that's why the delta V vector went the way it did. Okay, so that's my delta V vector. So you can picture the delta V that we're talking about in this question, and that delta V, that purple arrow now, but was a red arrow, is there towards the center. Okay, so this, you should be looking at this and saying, yeah, okay, great, I get it. It's the delta V is towards the center, the acceleration is towards the center, like we've been saying. That's the centripetal acceleration. So we also, in order to figure this out, need to look at what are called, like you think of as like radius vectors. So when you're at this position 1, the initial position, your radius locating vector in that circle is R1. And then when you're at your final position, you're at R2. And so you can do that the exact same way. You can do this one's listed as R1 plus negative R2. So this is a tip to tail, adding the opposite version of subtraction. I did it the 2 separate ways on here just to show the 2 different ways of doing subtraction. Okay, I could have aligned these things tail to tail. I would have had to use the regular radius vector though, mind you. Yeah, anyway, let's not bother. Almost looks like R1, R2. Just looking at why that one's called negative R2 instead of, like, R2 would have been that way anyways in there. It seems weird to me. Theta, R1, R2. If I had my R1 vector, I shouldn't have gone to this, I guess, but there's my R1, and then separate from that, if I had my R2, I'm thinking of it like that right now, but obviously last time I didn't. So if I had, oh well, it depends on what you define as the direction of the radius vectors, I suppose. There's a little bit of an iffiness there in my mind, but let's forge on for now, and it'll make sense in the end. So we're talking about uniform circular motion, right? Which means that the size of these velocity vectors is the same, right? So the V1 vector and the V2 vector, the sizes of them stay the same because we have uniform circular motion, the same speed all the time. Clearly, the radius vectors stay the same as well because they're the radius of the circle, right? So they are both isosceles triangles, right? So they're both isosceles triangles in this picture here, right? So you've got a equal-sided triangle here and an equal-sided triangle there. So they're both isosceles triangles, and we know that the velocities are always perpendicular to the radius vectors as well, even. Anyways, so The triangles, because they have the same angles, same relation in angles and so on, are similar triangles by side angle side, actually, if you look at it. Because in the triangle, let's grab this one. And so picture we have, side, oops, I want to grab the pen here. We got side, and we've got angle, and we've got side, right? Side, angle, side, similarity. So the triangles are similar, which means the sides are proportional. So if we've got these two vector triangles lined up, we've got this one similar to that one, both by side, angle, side, which means the ratios of the sides are proportional. So we can say that, the delta R value that we kind of are interested in over R, right, is equal to delta V over R. And I could say either one there because they're the same size. And so the ratios of the sides. So what we're doing here, just as a logic reminder as the steps along the way, is we're working towards getting acceleration. We're trying to work towards this delta V thing in terms of the geometry of what we're talking about. Okay, so you can see we're working our way towards delta V there in order to be able to figure out the acceleration. So since we're looking for this acceleration with delta V over delta T thing, we're going to solve for delta V. And so algebraically, I just multiplied out that whatever's in the bottom there, the V, right? So we're going to get the V times the delta R over R. V times delta R over R, just like I said. Okay, so we're talking about acceleration, so delta V over delta T, right? So I'm going to say delta V over delta T. There it is. Delta V over delta T. So this is conceptually now acceleration based on our situation, right? So we can, I just put it as a fraction version, right? So basically we've got the delta V times a 1 over delta T instead, just to kind of separate it out. Now this delta T is for a fairly large time interval in our diagram, right? We're looking at velocity here, and then way later on, we're looking at velocity over there, okay? So you picture like this situation where we've got this big path you take called delta S, that's the path length. And then we've got this like delta R, and over a long distance, these aren't the same, delta R and delta S. But as you go over shorter and shorter time intervals, this delta R straight line path becomes closer and closer to the curved path, okay? And over a really small angle, delta S and delta R would be essentially the same value. Okay, so the concept that's being invoked here is actually the main topic of the calculus course that hopefully is scheduled for next year in person. But what we're saying is, well, it's the same acceleration the whole time, right? So we know that any acceleration is equal to the average acceleration. What we're doing here is we're looking at, this is the calculus terminology, so if you haven't seen this before, don't stress out about it, but conceptually it just means what's the limiting value? What does this delta V over delta T become, right? What does it approach? What's the limit of its values? That's why it's LIM. What's the limit of these values as the time goes to really a small value, as that time interval goes to a really small value? So in other words, right, i.e., let's say delta V over delta T approaches what number or what value or what concept, right? Stop it, computer. What concept as delta T gets small? So as delta T gets small, that's what that's saying. So as time gets really small, as I said already in the other page, the delta R straight line gets really close to that delta S path length. Okay. So again, this curved line, the difference between it and the straight line is extreme. It becomes nothing when the time interval is 0, but for smaller and smaller time intervals, it clearly gets closer and closer to be the same. So what we're going to say is this delta S path length distance traveled thing. We're going to focus on that a little bit. So we're going to say, okay, obviously my speed equals my distance over my time, right? In this uniform circular motion. So this is actually V, like the uniform circular motion distance, or velocity, I should say, right? So we've got velocity equals distance over time. And then we can say, okay, well, for a really small time interval, right? This is now for a small time interval. Right? We have that that's the same as delta S over delta T. So we can solve for delta S itself, the path length. Okay. So in our formula here, conceptually, I'm showing the idea here that as we actually make this happen, right, as we actually make the time go to 0, this thing becomes delta S, which we just showed is equal to velocity times delta T. There's a lot of like conceptual meaning here in this slide, and so this me walking you through it is important if you haven't had calculus, especially. But that's what that means. Is like as we're letting this go to 0, then this just becomes delta S. So that's why the limit stuff can disappear. So we're saying, oh, okay. So in other words, we've got this for really small delta T's, right? So some neat things happen. We've got 2 time delta T variables, so they can cancel out. And that leads to, what do they have here? Like that's the next part. This delta T's cancel out, so that leaves you with just V squared over R. Okay, so that's the acceleration. You can even actually consider it as a vector because you can just say the direction's always towards the center. The textbook typically just calls it like the magnitude of the acceleration, and then the direction's defined by towards the center. Kind of like in the magnetic field stuff. Often they didn't call it vectors because it depended on the hand rules. Okay, but acceleration equals V squared over R. That is the resulting formula from our development. Okay, and it relied on lots of little things, right? The geometry of this, the triangles we got from these vectors. We had to talk about the radius vector triangles because we needed to talk about distances in order to be able to talk about where was my slide here to velocity was distance over time, and so on. But yeah, we ended up getting V squared over R as an equation for acceleration. And then to get the force concept is super easy because it's like, well, F equals ma. So if centripetal acceleration equals this, then centripetal force equals mass times it. It's just the second law. So this one here is the one that I gave you in the context of the electromagnetism unit, because we wanted to be able to actually talk about the motion that charged particles go in when they're moving in a magnetic field. So we should add to our equation sheet the V squared over R as well. So somewhere in here it just says equations. I forget whether I added the mv squared over R yet in here. I think I did. Any questions about that development though? Like I'm hoping you can look at it and agree like, oh yeah, okay, that was a lot of very logical steps, bit by bit. Not necessarily steps that you would have been able to come up with on your own, myself included in that one. That was, like basically this is like a proof that I've seen, or a development to call it, I guess more so, that I've seen, and now I'm able to, show you. But don't stress out about the idea of being able to produce that yourself. Just be able to walk through it and understand it based on what you know is going on here. So AC equals centripetal acceleration. All right, so both of these we could add on, vector-wise. We can say vectors towards the center of the circle, right? So I can even call it vectors because we know it's towards the center of the uniform circular motion. So add that one in there. And is there any other equations we've forgotten to add in? I feel like maybe there was. Anybody? Just remind me to, every time we come up with a new equation, remind me to load that up and we'll add it in. I'll, if I come across it, I'll add it to it and point it out to you later.
Could you go back to the diagram for a bit? I just missed a couple of pieces.
This diagram, you mean?
Yeah, the circle one.
Yeah, for sure. Do you want me to explain anything from there, or are you just jotting stuff down?
I'm just jotting stuff down.
Alrighty.
Okay, that should be good. Thanks.
You're welcome. All right, so now we're actually gonna be able to like do calculations to do a circular motion, right? So we have a 4 kilogram mass tied to a string, and it's in uniform circular motion horizontally, so it's a little bit easier to start out with a constant velocity of 3 meters per second and a radius of 2. So you can tell, like, I've given you the things we need, right? I've given you the radius is 2, and I've given you the velocity is 3, and I've given you the mass is 4, and so on. Notice that for acceleration, you don't need mass, but the amount of force needed to cause that acceleration, you need mass, right? There's lots of questions coming up where, like, sometimes they won't give you mass, and it seems harder to do the question, you know, because you have to like use m in places where you would normally get a number, but eventually you get like m's on both sides because you'll have, I'm not sure if it comes up in this question or not, but we'd have like fc equals the especially if fc equals fg, that's more in the vertical one coming up. But you'll have like mv squared over r will equal mg, and so it's like, oh, mass doesn't matter, you know. So I'm always a little bit weirded out by that myself too. It's like whether if they give you mass or not. And there's a homework question I worked out where I put on at the beginning like m, and I was like, probably not needed, and sure enough it wasn't needed, right? So I did the calculations without the number. But then in part D, it said, well, what's the tension force? And like all of a sudden now it's like, oh, I need the mass for that part. Okay, so watch for that in the homework solutions when you go through it. I'd recommend looking at the homework solutions even if you feel you got the answer right, just to see if there's anything else that you might want to do, like be able to work without a mass value. But anyways, we want centripetal acceleration. Obviously, that's v squared over r. So use the equation, plug numbers in, get a value. Okay. So this one clearly doesn't need mass because mass isn't even in the equation. But what I showed a minute ago is going to come up in the vertical versions when gravity is providing the force. So we got that. Determine the centripetal force needed for the motion. So obviously that's just a mv squared over r thing. We could have started with mv squared over r, I suppose, right? We could have said, oh, fc equals mv squared over r. This is or, you know, mv squared over r, and plug in all the stuff. So put in your 4 and put in your velocity of 3 squared and divide by the radius and so on, and it'll give a value. But the other way is, well, if you already know the acceleration, right? So we have acceleration AC equals 9/2. It should just write it as 4.5, I suppose, at some point, right? So let's do that. Right, so if I know this is 4.5 meters per second squared, so we know acceleration leads to F net, right? F net is what FC is. I wanted it to be a different color there for emphasis. Hang on a second. F net, exclamation point. F net is FC. Anyways, so that gives you mass times acceleration. So mass times the 4.5 and gives you 18, which is clearly what this would give as well. okay? So I feel like in the context of this lesson, you might find the red one easier to follow because, oh, we're just using that new equation. But clearly this is an important right here. The idea that acceleration leads to allows you to get net force is a very important concept for this course, and I cannot convince it to change colors, except sometimes I wonder if sometimes I assume it's the computer doing weird things, and then other times I realize, oh, I clicked on the wrong one repeatedly. Anyways, that's what happens when a computer does do weird things lots of times. Or maybe it's just always me. Any questions about that so far? So we were able to get this actual centripetal force, right? Now they want to know the tension in the string. Well, it's a horizontal motion. The tension in the string is providing the centripetal force. Like it's just, that's all there is on it, right? So there's, think of all the forces that are on this thing. The only force that's on it is the tension force. So I'm showing it on some purpose to remind you, like F net equals all the forces added up, but there's just the one force. So tension is really just that 18 newtons. Okay, that's for horizontal, of course, right? So in the next question, we're going to see vertical stuff, and we're going to remember that vertically we have to, what was it, the PDF file? Vertically, we have to think about gravity as well, right? So we're going to actually use that in the next example. Anybody need anything from this page still? All right.
Don't think so.
Crickets. So I hesitate to even show you these ones because to me they're completely unnecessary. But sometimes just for convenience, they'll give you information about the uniform circular motion based on the period of the uniform circular motion. So remember, period is just the time for one rotation. Right? And so basically that's the equation. I'll show you why it makes sense. And then knowing that period equals 1 over frequency, that becomes this one, right? So this, remember, frequency, of course, is the number per second, right? So they're going to give you period or frequency information. You can just calculate, the velocity based on this concept. So for example, if they give you time for one rotation, so maybe it was like one rotation maybe takes 2 seconds. So for example here, period equals 2 seconds, right? You can just get velocity. Right? Velocity equals delta d over delta t. And the trick is to realize that the delta d is a circumference. Right? So circumference, of course, is 2 pi r, right? So you end up with like a 2 pi r over the 2 seconds. So in this case, you can see like pi r is going to like go away, right? So can you see why we end up, the 2 is going to go away, that is. Can you see why we end up with a pi squared? We end up with a pi squared because this is going to go into like a v squared over r equation, right? So we're going to have a pi squared when we put it in. It's going to become, it's going to become the 2 pi r squared per the 2, So you can see how we're going to end up with, actually, over the 2 v squared over r. Oh, yeah, it's not, it's an r down there, that's why. Right, so that's v squared, the top stuff. And then, I forgot my 2 in the thing. That's what I got to do. Over there. Right, so that'd be over 2, but really it should have just canceled out. And we'd have the over r. And so right now, we should be able to look at these equations and say, oh, okay, I get it. So the squared of the pi is logical, it's there. We have an r squared, but we have a divide by r. So the fact that you have just an r there should make sense too, and so on, right? Even the 4, the 2 squared, right? This came from the 2 squared. So these equations come from just knowing what period and frequency mean and knowing that we're traveling in a circle and circumference is 2 pi r, right? So that's what is shown down here, just all blurted out on the page. But so there's your distance over your time, that's your speed. So this is v, right? right? So that's V. And then, like I said, just recognizing that big capital T is the time for one revolution, so it's your delta T and so on. When you put the 1 over frequency, it becomes 1 over frequency in the bottom squared, which just inverts and multiplies, right? So think of the invert and multiply leads, of course, to this thing. So I don't use these. Like you'll see in my solutions that I don't use these, and I actually recommend that you don't either, because you'll have much better understanding of what the heck you're doing if you figure out velocity. So I'm showing them to you because you might end up seeing a question, or maybe like have a teacher at some point in university or whatever that says like you forces you to use them or whatever, so you should be familiar with their existence. But you can just get the velocity and use your equation. Okay. So I hesitate to even add these onto the equation sheet, but I will just screenshot it onto there. Maybe I'll just show, open that. I don't know, on the equation sheet. So here we go, equation sheet. Continued. Oh, I should suppose put it after the uniform acceleration stuff. Kind of mixing things up a bit here, but organizationally, maybe we should have. I'm almost wondering if I should copy this to have it lots on here, so you have the circular motion stuff and the silly frequency and period version of it. There's enough equations out there. There's enough concepts out there that physics explains, which means that there's enough equations out there. We don't need to memorize more of them, for goodness sakes. So in the equations above, vector symbols have been omitted. We're talking about the directions towards the center. I've already mentioned that, so I'm just jumping ahead here. So problem solving with centripetal acceleration and force. We've already started doing that. I don't know why it's there now. Vertical circle. Here we go. Okay, so vertical circular motion. So make note of that distinction now, right? Vertical, which means FG is a factor, right? So what have they told us? They gave us some information here. So we are given, we have a mass of 0.45 kilograms. They gave us a length of the chord for the circular motion. So I know it's R for the radius of the circle that results. Because it's uniform circular motion, UCM for short. They told us even the velocity of this thing, 5 meters per second. Okay, they're asking for the FT. So asking for the magnitude and the direction. So in other words, they're asking for the vector. Okay, automatically you have to give the magnitude and direction in that case. So part A, they are asking at the top for that, right? So the first thing I would do if I were you is I would sort of help visualize the situation here and be like, okay, so we're at the top of the circle. I've got a gravity force down, obviously, at the top of the circle. And I've also got a tension force of some sort. So I'm going to draw it too. I have an FT of some sort. I don't know what the sizes are. Doesn't matter at this point. I'm just going to figure it out, right? But I know they're both down. So we know it's uniform circular motion, right? And so what do we know? We know that they're given M and R and V, right? We know the centripetal force is mv squared over r. That's the kind of the first thing to do here. So we can actually figure out what the centripetal force is. And so that's obviously just an easy calculation. If this question had just said, what's the centripetal force? We would have obviously just done that. It would have been an even easier looking question. Well, we'd be done at this point, I suppose, right? So it would be easier. Over 5, I didn't forget the square there. I just don't want to make the screen bounce around. So I need to do this first. All right. So we got our mv squared over r. And so we can just calculate that. We've got a 0.45 times a 25 from the squaring there divided by 1.2 gives me 9. My screen's moving around on me. Whole laptop slid when I tried to draw on it. 9.375 meters per second squared. Just note here, I'm going to keep all 4 calculations, right? Keep all numbers for calculations. In the end, I'm going to be rounding to 2 significant digits. You can see they're all 2 SDs, right? But I'm not going to round to 9.4 right now because that'd be just unnecessary rounding for the rest of your calculations, right? So what's the next step? The thing you have to start to write, same as the importance of knowing like acceleration led to FNet, you know, especially if like there was no acceleration, then you know the net force is 0, all that stuff, how important that was. A very similar important thing to always be able to recognize is that this is FNet. Right? That's FNet, right? So basically what we're doing now is we're saying, you know, it's uniform circular motion. And so we're saying, let's do it like this, FC equals FNet, of course, right? And now we're looking at what the net force is comprised of. What forces are there that make up the overall force on this object? And on my free body diagram, I can see that there's a tension force and there's a gravity force. Right? So that means that I've got a 9.375 equal to the tension force we're looking for, plus whatever that gravity value is. I'm going to say plus, I'm meaning and. We have the tension force and, which is a plus sign. We have the gravity force, right? Is gravity up or down in this case? Of course, you can tell it's down, right? And that's where we're going to have our mass. This is just mg, of course, right? So I'm going to put my mass in. And I'm going to put my g value in, minus 9.8. And I'll point out that, of course, the minus is in there, but it's down. What sign should be here? What sign needs to be there? Positive or negative? Is the centripetal force up or down when we're at the top of the circle? Running out of time. Can you not see that the centripetal force would have to be towards the center of the circle? So the sign would have to be. Anybody home here? We've got 5 people to choose from here. Come on. It's down, isn't it? Wake up. That's a minus there, right? So this negative there has to be there, right? We're putting that in on purpose because it's down. All right, so then that gives us a tension force. We just algebraically solve out. I'm going to get the numbers here. So I got the 9.375 as a negative number. I'm going to add this stuff to it. So I'm actually going to store that thing in my calculator. I'm going to do 0.45 times 9.8. I have 4.41. I have to add that to that negative number. So in other words, I'm subtracting 9.375 from it, giving me a negative 4.965 newtons. Okay, at this point, because I'm claiming my final value, I'm going to round to 2 significant digits, which means I have to round that up to a 0, like a 10, which rounds that up. So I'm looking at negative 5.0 newtons to 2 significant digits. Okay, that's the tension force at the top. Questions? So the next step would be, of course, to do the tension at the bottom. And I can almost just clone this entire page, change the diagram a tiny bit, just to. So I'm going to do that. So now we're going to say at the bottom, just to illustrate that this is the exact same process that helps do the job, right? So now we're going to say part B, we're going to be at the bottom. Part B at the bottom. So for the bottom, I need to look at the bottom of this thing. So let's just get rid of all of that because it's easy enough to redraw. And I've got a circle there. And let's move that up a little bit so I can focus on the bottom here. The bottom, of course, I've got a gravity force. And I've hopefully, obviously, I'm going to have a tension force up, right, of some sort. So those are the only forces that are on it. So this is the same, right? So basically, what do you want to say? Like, obviously I don't need to redo all of this, right? So this is still true, right? So you wouldn't actually redo that calculation. You'd be like, well, of course, the centripetal acceleration is still 9.37, whatever. But the centripetal acceleration is up, right? The centripetal force that results and so on. I said acceleration, it was actually force. Now we're going to say, ooh, this is actually up. Because we're talking about being at the bottom, right? So now that's a positive value here. Actually, I gotta get a new number for that one, but so we need the new number from this thing, and that will be from adding those two numbers. I'll have to redo all this, I guess. So I have that 9.375. I'm still adding because gravity is still down, of course. That didn't change. So we're adding that. So store that thing 9.375, 0.45 times 9.8. I didn't have that number stored. So add that to my 9.375. Gives me now 13.75. 75, yeah. All right, so that's 13.785 newtons. Notice it came out naturally as a positive from our calculations. And so that leads us to an answer here of to 2 significant digits, right? If we're going to 2 significant digits, we actually would just say 14 newtons. And this one's, of course, this one's 14 newtons up. And the one before that was a minus. And so awkwardly, we have to sort of say IE down, right? So your 2 ways of doing this is to say like IE down, but really the full way to do this is to say 5.0 newtons down. You ditch the negative and claim that it's down.
Mr. Horn, I was just wondering, like, the difference between the horizontal circular motion and the vertical circular motion. Like, how could you have one without the other?
So what they envision for the horizontal stuff is that it's on a slippery surface. It's on like on a pond or something, and so it's undergoing uniform horizontal circular motion. And let's add that in. It's like on a frictionless surface. Does that make sense to you?
Yeah, that one does.
Okay. So we can have it on a frictionless surface, and so you're zipping around and around horizontally, right? And the fact that there's a gravity and a normal force always balancing out is irrelevant. All we're really focused on is the fact that there's a tension force. Let's go purple for that one, right? The one we really want to talk about is that tension force. Goodness sakes, purple, right? FT. That's the one we were looking at. What's that tension force in the string? And so that's what's providing the centripetal force and so on. The fact that, like I said, the fact that there was a gravity force and a normal force always balancing out, was irrelevant the whole time as far as the circular motion goes. In the vertical case, of course, as you've seen here, the gravity is actually contributing to the, it's actually causing, helping cause the circular motion. Does that answer your question?
Yeah, it does. I was also like kind of confused about it. So the horizontal has no bearing on the vertical at all, because like if you look at something spinning like, I don't know, around something in the air, if you look at it one way, like it's still horizontal, right?
So we have it's going to be sitting on a flat surface with no friction. Okay, so I don't know what you mean, actually, to be honest. I'm not sure. Are you complicating things by trying to think about like something hanging on a string and then going in horizontal circular motion? Is that what you're trying to visualize? Because I don't want that. It's not hanging from a string and so on. It's actually just on a flat surface, and it's literally just going around in a circle on a table, right? And so we want to know what force is towards the center, what tension force is needed towards the center.
Yeah, I think you're right. I think I'm just like making it way more complicated than it has to be.
Yeah, we're just like, if gravity didn't exist, pretend gravity isn't even a factor at all, because it isn't in this case, right? Just, what kind of force must be needed? So you're way out in outer space somewhere, floating in a spacesuit, no gravity to be found because you're super far away from all masses, and you're whirling a stopwatch around by a string. What's the force in the string needed to do circular motion, right? And so that's equivalent to this frictionless surface situation. The vertical, of course, like I said, the gravity kicks in and provides some of that force and so on. And so this is the solution that was already there. Notice that I never put the centripetal force on the diagram. Like I think I showed, the direction of the centripetal force, but that would just be the result of the addition of those two things, right? You don't list it as a force on there. And so we had these two separate diagrams. They showed gravity plus tension force here, which I preferred to show both of them, of course, because you can see they're both there. And so they calculated it out and got the 5 and the 14 like we did. Okay, so I'll just delete this stuff so that you see the official out version of the solution, but similar to what we did. Yeah. So therefore statements in the end, of course. So this we have a car going on a flat road, goes around a curve, turning a corner, right? And flat road is important. We're going to actually look at banked corners soon. So it's a flat road. We don't have to worry about, in the end, we'll have to worry about gravity acting towards the center of the circle. That's when we do banked corners, but this is simpler. Says the coefficient of static friction between the tires and the road is 0.5. What's the maximum speed the car can have to make the turn successfully? So let's think about what we're given here and think about what we can do, right? So we know we are given some things. So we're given mass equals 1,200 kilograms. We're given the radius of this uniform circular motion we want to go in is 32 meters. The coefficient of static friction was given as, they're saying static friction, but they should be saying like rolling friction, which is similar to static, but it's actually not quite the same. So that's just a correction that they should have made better. But yeah, so they're saying here, like what speed can we have? So I might put it up here, because I think from this, you can sort of see we're going to be able to say, oh, I know that FC equals mv squared over r, right? That's a new equation that we're working with, right? The old stuff that we're going to have to do first is we're going to have to figure out how much friction force there is, because this, of course, is provided by friction, right? The friction's giving the force towards the center. So we'd have to say like F equals mu Fn. I wouldn't necessarily expect to see the full analysis about the normal force, but it goes like this, right? Acceleration in the y direction is 0, so the net force in the y direction is 0. And so, the 0 equals the gravity force plus the normal force. And so the normal force equals the negative of the gravity force. And so the normal force equals mg, right? Because g is a negative value, so it ends up being positive like that. So anyways, long story short, we can get the friction force, 0.50, which is, of course, a lesson we've done in grade 11, but reviewed recently. So we're going to say 0.50 times the mass, the 1,200, and I'll just move things around to make room for myself here. Extend that arrow in a minute, and the g value, 9.8. So we can get how big of a force is available for uniform circular motion. 0.5 times 1200 times 9.8 gives us 5,880. Okay. So that's the force that's available for uniform circular motion. Right? So it's asking the maximum speed available. Obviously, that the biggest centripetal force you can have is the 5,880. Right? Significant digits. If we're still paying attention to that, notice this is only 2. So really, we're only keeping 2, but I'm going to keep all of them for calculations. Still, as always. So over here, we're going to say, okay, so we've got our 5,880 for accuracy in my calculations, and we have excess rounding, right? We've got the 1200. What speed do we get? Is the v. The radius, of course, the 32. And so, bada bing, bada boom, you get numbers. So I'm going to multiply the 580 by 32. I'm going to divide it by 1200. And I'm going to square root it. So I'm not showing as much of the math anymore. I'm hoping that we're getting to the point where the algebra isn't a crippling confusion for anybody. Okay, but obviously, I would have like I said, multiply by 32, divide by 1200, take the square root, and so on. But algebra leads to 12.52 meters per second. If we're claiming a final answer, we can trust 2 digits only, right? So what does that round to? Trick question, actually, a little bit here. Does it round to 13 or 12? By the special rounding rule, it rounds to 12 meters per second, right? And yeah, notice that this is speed, not velocity, right? So it's like to get directions, it's obviously like tangential to the circle, right? So I'm going to say just tangent to the circle if we wanted to think about directions. I suspect the solution here might say 13, but that's okay if it does. Yeah, they say 13. They just didn't know any better. Okay. So, questions? Canceling the mass. What did they do there? Is this a different question? Car moving flat surface. I guess we didn't need the mass. Let's look at that. Yeah, because we have, if I analyzed, let's look at that actually. Is mass needed? Kind of a neat thing to look at, right? So because we could write the friction as, so we got FF equals FC, right? And we've got mv squared over r. And here we have basically like mu and mass and 9.8. So I didn't notice it earlier, but absolutely we could have done this without the mass of the car being known at all. Just strange. They gave it to us to make it seem like they make it easier to actually do. But notice that these numbers, you got the mu, you got the 9.8, you've got the radius, and so you can get the v. The answer is no, you don't need it. But would this question have seemed harder? Probably, right? Because when you looked at getting the friction force, you wouldn't have been able to say a value. This would have had to have just been, whatever that number is, 0.5 of 9.8 is the 4.9, right? So it would have had to have just been 4.9 m, right? And then when you set it equal in here, this would have been 4.9 m, and this would have been m here, and so the m's would have canceled out, and so we'd be doing 4.9 times 32, and then rooted, and guess what? It gives the exact same number, 12.52. Okay, so I feel like I should. I'm going to change this to just be all blue, so the purple stands out as the is mass needed stuff. So first we looked at that, and then this is the mass needed stuff. And this could just be red or blue or something. I don't know. Anyways, questions? Yeah, I think that works. Okay. So there's lots of other examples worked out in this lesson. I'll just leave them for you to be able to see. This is a world in a horizontal slippery surface business. So it's another horizontal one worked out. We have a Ferris wheel, it's a vertical circular motion question. They're worked out. So there's extra examples worked out there for your viewing pleasure. All the way down here, lots of them. And then that's the review of, oh geez, that's the review of that position, the forces and so on, but it's just another vertical uniform circular motion question. So many other examples, all just records of them worked out there for you. The questions to do with this are those. And I have the lesson 36. Let me just check here so you know to look for it. I have the lesson 36 solutions ready to go as well. It's a little bit, there's honestly a little bit, it's a little bit heavy for numbers of questions. So watch carefully and just like look and start skipping questions, right? If it's yet another question where you're like given F or given B and M and R, calculate FC, just basically set the question up and move on, or just skip it if you can tell it's the same. Use the solutions that to help you with that judgment. So this lesson actually won't add as many questions, I think, if I'm right. Maybe not, but we'll get through it. So this is just an example worked out again with uniform circular motion stuff. So I'm just going to leave that for you to look at, just like those other ones. So there's tons of examples to look through for help. Previous opening questions from the day and so on. Okay, so all this stuff is just solutions that you can look through if you need help. What I want to focus on is a cool ride that you've probably had a chance to be on called the Gravitron, not to be confused with the graviton, which is the exchange particle for gravity that we're still trying to find. Gravitrons are easy to find out. In fact, actually, Mrs. Horn actually saw on some kind of social internet thing or whatever, but someone was selling a Gravitron ride. I'd have to yell and ask her how much it was. It was like $70,000 or something. Someone in like the States, somewhere in Tennessee, I think, was selling a Gravitron ride. Wouldn't that be amazing to have that in your backyard? It's like, I feel like puking. Let's go in the Gravitron. So the Gravitron, if you haven't been in it, spins around and around. You go in the ride, and you're standing against this wall, right? And it starts to spin really, really fast, and eventually the floor drops out from underneath you. So you were having to stand on the floor. The floor drops out, so it makes you aware of the fact that you are stuck to the wall. So this person has like turned upside down. This person's doing like a sit-up, which is very difficult to do because you'd be like sitting up against that centrifugal force, which isn't wrong to say because they're in a non-inertial reference frame, right? So some people think that centrifugal force is like a 4-letter word, but it's not. It's many more letters than that. And it's actually okay. And this guy, I love this meme. It's like riding the Gravitron like a boss. Like this person's clapping, it's like the person stood up and like standing against that circular motion force that they're feeling in that non-inertial reference frame. So Gravitron, is it still active or do I have to get my, YouTube sucks. All right, well, it's good, but I wish they'd just leave their links alone. So I will undo my keyboard and I don't know if we need to see this video, mind you. I have just Gravitron. Probably not that big of a deal. I've explained it enough, I think. But Gravitron. Oh, I can't type on my keyboard. Ugh. I have a separate keyboard that's easier because I have the screen flipped upside down or towards me so I can write easier, but Gravitron. Gravitron FLV. Should be that one. What does it show? think it's literally just a picture of someone in the ride, or video of someone in the ride. Yeah, here we go. So the door closes, everybody's standing on the floor. Okay, so get this thing spinning. Oh, I guess I went too fast here. Is it spinning yet? Can't really see when the floor dropped out, but that's the ride we're talking about, just so you know what we're talking about. Anyways, like I said, maybe not worth plugging in the video for that. So there's a description of it and so on. There's going to be an assignment question to do with this ride. So we have a Gravitron, and it causes riders to go in uniform circular motion with a radius of 3.5 meters. The riders are leaning up like a flat vertical wall, just to simplify things. It's not quite flat in the video as you saw, but if it was, what would the friction coefficient need to be between the actually no, the friction coefficient is 0.4. That's a different way I could do the question. If I told you the speed, I could ask what the friction would need to be. Question is, what's the minimum speed this ride can go at so that people don't slide down when the floor drops out? So we've actually covered all the stuff that's needed for this. We understand circular motion, we understand friction. That's an assignment, okay, for you to do. So let's have that due by the end of, I was going to say tomorrow. We do have a help session tomorrow afternoon. So yeah, let's do that. It's kind of like a homework question to do with it. You know what? End of Monday. Give you a little more time. End of Monday. And in end of Monday. Do end of Monday. All right. So let's leave that there like that. Just because I know that there's some questions I want, obviously you're going to want to do first on the from the homework to get good at these things and then start to tackle it. Don't just ask me how to do it in the help session. Do the homework first and get to know how to do things and then tackle it. Just some interest ones here, the uniform circular motion in the world around you. If you go to India, maybe the link might still work. Again, what do they do to their links? All right, so we're looking for my wall of death. Sounds interesting, right? Wall of death. So picture the uniform circular motion and forces and so on involved in this wall of death. So people are like, they start out at the bottom driving and then they end up being able to drive around and around this big wall of death circular motion thing, and people watch. And then these cars get driving. So the car drives, turns, drives, and eventually is up there as well. So you can see why they call it the wall of death. We've got cars and motorcycles all going in unison. Oh my God. Yeah. So luckily, this is physically possible because these cars and the motorbikes travel at the same speed for this uniform circular motion, thanks to all objects falling at the same rate due to gravity. Otherwise, it would be even more a wall of death because a car would be going like 3 times or 10 times as fast as a motorcycle because it weighs 10 times as much. This is another Gravitron ride. Let's see if the link works. I don't know why I'm bothering. The links have all changed apparently. Let's see. This one's a scary one. This one works. Yay. So this is another type of Gravitron ride where they have a Wonderland where it flips up vertical. And so you'll feel pressed into the wall. And then it flips and goes vertically. You can watch this horizon. So you're still horizontal, but now it's starting to go. You can see the ground, then the sky. Ground and sky. And I'm actually getting a little motion sick thinking about this, watching it. Oh boy, that's interesting. Here we go. Sky, ground, sky, ground. So they're flipping that one to be vertical, uniform circular motion. Anyways, so yeah. So now you'd be thinking about the vertical stuff for that one, right? And what we've tackled. So the idea is all the work you're doing tonight in the homework, is very applicable to all these things. Okay. So this vertical circular motion, you should automatically be thinking about the fact that there's gravity and there's a force from the, there's gravity and there's a normal force, right? And as long as there's more force needed for this circular motion, if there's more force needed for specifically actually the circular motion at the top, right? Than gravity, then you stay on the surface because the surface needs to actually push on you to make you travel in that circle. That's that whole water in the bucket thing. If you spin the water bucket fast enough, the water stays in the bucket because it needs more force towards the center, towards your head, than gravity provides, right? So that's something to be able to do. So if we're applying this in this situation, we've probably played with lots of people. It was a common toy back in the day. Maybe it's not as common anymore, but these little flexible tracks with little toy cars, like dinky cars, you might call them, with the yellow track and the little loop-de-loop business. These are like full-size versions of loop-de-loop things. So we've got Bob Burnquist doing the loop-de-loop. Let's look at Bob here. I'll just type it directly. Bob. I think it's the only video I have, but Bob being the name. Oh, maybe there's some other Bobs. Look at that. Bob Burnquist does the loop-de-loop. There, now you know. So this is Bob Burnquist doing the loop-de-loop, apparently on a skateboard. There you go. So he's going to do loop-de-loop. Oh, slam. Oh, slam. Yay, he did it. Right? So when he's doing that loop-de-loop, that's what we want to analyze. Okay, this actual idea of this loop-de-loop. And so when he's at the top here, the gravity that would make him fall on his head isn't strong enough to actually make him fall on his head, because instead, as he's accelerating down, he's also going sideways fast enough that he ends up over here. So by the time he falls to the middle, for example, he's over here. And by the time he would have fallen to the ground, he's already down there by, his sideways motion and so on. So you want to picture that. Okay, so this is a loop-de-loop that I certainly have never done. Oh, that looks bad. Oh, goodness. There we go. Well done. So sometimes it goes well, sometimes it doesn't. So fifth gear, the show, loop the loop. They check this out. So loop the loop. Oh, my other keyboard. Loop the loop, fifth gear. They built a full-size track for a car and then analyzed out, looked at what kind of forces you'd need. So here's the plastic toy track that I'm talking about.
Hot Wheels loop the loop. God, I'll send one down. Here we go. Yes. What we wanted to know is, could you do that in a real-life, family-sized car? Yeah, we gave the job to our friendly neighbourhood stuntman, Steve Trulia, but we wanted some questions answering first. How fast would he have to go? Would the car stick to the road? And would he black out under the G-forces? Steve Trulia is the man facing this monster challenge. As Fifth Gear's head of danger, he's rolled, crashed, and crashed again in numerous Fifth Gear stunts. But even by these extreme standards, nothing can prepare him for our most dangerous stunt yet. Clearly, scaling a toy up to a record-breaking 40 feet high using 5 tons of steel and a real-life motor was going to be dangerous. So we sent Steve to Cambridge University's Dr. Hugh Hunt to find out how fast he'd have to go. Now listen carefully.
So what he's doing there is he's calculating what speed you should enter the loop-de-loop. You don't need to go to Cambridge and see a professor about that. That's grade 12 physics, believe it or not. So let's go through it. Let's calculate out what speed it would have to be. So we're going to go through this 40-foot high loop-de-loop. So that means we've got like a 20-foot radius, which is equivalent to a radius of 6.096 meters. Just do a conversion to get meters and divide it by 2. But anyway, so we've got a radius. The video, once he does all his calculations, magically says, "Oh, the answer from above, from the physics gods, is 18 meters per second." But we can do this ourselves, at least approximations, which was exactly what he would have been doing. So conceptually here, you likely, the minimum speed here, let's look at the minimum speed idea. The minimum speed would be if you got it so that the centripetal force needed would be equal to the gravity force. But that would leave there being no normal force whatsoever. So when the little toy car goes through the loop-to-loop, right? That's probably okay because it's just going to be like super lightly, you know, barely any force between the car and the track going, right? For a real life car, I suspect you're probably not going to want to gauge it that way because you'd want to have some normal force between the car and the road because you want to be able to steer the thing, right? You need to have some friction in order to be able to. So you wouldn't want this for the stunt because you'd want some contact force between the car and the track so you can actually steer and maintain control. Okay, so we're not looking for the minimum speed. I think we'd be looking for, I'm approximating and analyzing with you here, that I think we'd want the normal force to be equal to the gravity force still. In other words, have it be the same as normal at the top, like normal driving. So the car's driving along the road, how much contact there is to the ground there is going to be the same as the amount of contact at the top, okay? The amount of contact force right here is going to be a lot more because there's going to be additional forces to provide that circular motion. Okay, so it's going to be a huge force right here, but then it's going to have normal force there, and then bigger forces, and then, you know, picture that. Okay. So we're saying that the net force, of course, is the centripetal force. We know there's a gravity force, and we know there's a normal force, equal. So I'm going to say 2 mg's. Notice we don't need mass. The mass of the car, this professor in Cambridge or wherever they were, hopefully didn't say, okay, so how much is the mass of the car and what's the mass of the driver and so on, because you don't need it. Okay, all objects accelerate at the same rate. The only, I should say though, when they're building this thing, when they're building this metal structure, they need to know the mass of the car then, because they need to know how strong to make this. The kind of forces that would be involved depends on the mass, but the speed you need to go does not depend on the mass. So my first the first result I'm getting is that the centripetal acceleration needs to be like 19.6 meters per second squared. So that's just your centripetal acceleration needed. It's not the 18 that they're talking about, right? So 19.6 meters per second squared is the centripetal acceleration we would need. Any questions so far? This should be making sense to you. And if it's not, you need to ask questions. Right? The idea that we don't want just the centripetal to equal to gravity, because that would be like free fall here, like weightlessness. So there'd be very little contact between the car and the track. That'd be dangerous. So make it so that the normal force is sort of the normal is what it would be, right? Gravity. And that leads to this calculation saying, oh, so we want a centripetal acceleration of 19.6. So I hope you're looking at this and saying, well, okay, wait, I know centripetal acceleration equals v squared over r. I know the radius. I know this triple acceleration I need, so I'm just going to get the v. It's not actually that hard of a thing. Like they went to Cambridge to get that. They could have just gone to a high school and asked for the physics teacher, right? But anyways, there's no other special physics involved. So let's take a look. We've got our v squared over r, boom, 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 and we get a velocity of 10.9, I'm saying here at this point, which is not very close to the 18 meters per second, but this assumes uniform circular motion. As the car, this is where it gets a little tricky, as the car goes up the ramp, right, the kinetic energy is going to convert to gravitational potential energy, so the car is going to slow down. So if you sent the car in at 10.9, it's going to slow down as it goes up 14 feet in the air, right? 6, whatever it is, 12, actually 40 feet in the air, right? 12 meters in the air. It's going to slow down a lot, right? So it probably wouldn't even actually get to the top if it was coasting. So we're assuming here that the engine, either it's just coasting or the engine can't maintain speed. It's not exactly the most impressive looking automobile they're using here, right? It's not like a high horsepower vehicle. So the assumption would be that, you know, obviously you're not going to be able to like regulate the gas and get enough throttle to make it maintain speed. So for simplicity, we're going to let the car coast through the ramp, which is very similar to the person, what they would have done. Okay, so this is not enough speed for it to coast through the ramp. It's just the speed that we would need to have the whole time. So we need to have this speed at the top. So we're going to coast in at a faster speed so we end up at that speed at the top. Okay. So luckily we understand kinetic energy situations, right? So my my kinetic energies, my change in my kinetic energy. So I'm going to have my speed that I want to have take away the speed I want to have at the top, right? So basically I want to have enough speed left at the top, the 10.9. And so I've got a final speed and initial speed here of 10.9. That on this side, well, actually I should just use the whole equation here, but I've got my change in my kinetic energy, which involves my speeds. And then I've got my change in my gravitational potential energy, which remember from grade 11 was mg delta h, right? The delta h is that full height of 12. My g is in there, boom, boom, boom. I can calculate out 18.9 meters per second, right? That's for coasting. So perhaps the car has some energy. Maybe they looked at what the amount of force the car can do. I kind of doubt it, to be honest, because they, you know, like how much, what kind of cruise control, how much RPM, like horsepower the engine is gonna apply. They probably looked at it as a coasting in thing, but maybe they looked at a little bit of engine power and, you know, approximated to 18. I'd probably quote 19 or 20 just to make sure I have enough speed if I was the person being asked what speed we should go in at. But pretty close to that 18 that they're saying, right? So I hope you see this and think, oh, it's kind of cool. Like we can actually use the physics that we've accomplished to describe interesting things. Like they make a TV show about this. This is an interesting episode of this TV show. And it's all the analysis is based on multiple things we've done, including the gravitational and kinetic energies and so on. But it's neat. So the video says he would experience a maximum, if you watch the whole video, it says experience a maximum G force of 6 Gs. The centripetal acceleration at 18 meters per second would be 53.14 meters per second squared. If you divide by 9.8, right? If you divide that by 9.8, which is G, right? Come on, computer. 9.8, that gives the 5.4 Gs, 5.49.8 basically, right? So they're saying it experiences 6 Gs. Well, you have to remember that at the, if you're feeling Gs, right, at the bottom, you're going to have additional force to push you towards the center. So you've got the normal G that you are, like everybody right now is feeling 1 G, right? And so go back to that unit from grade 11 where we're saying like, you know, what force do you feel and so on. Right now you're feeling 1 G anyways. You need to feel, you know, you need to have these 5 Gs up. So you're going to have to feel 6.4 Gs up in order to actually accelerate at the bottom for that maximum force to be felt. All right. So that is it for that part. So with Gravitron, we got assignment 4. Let's do Monday. Wrong keyboard. Do Monday. End of Monday. End of the day. Do end of. And what else here? Just group that. The questions to do with uniform circular motion and that are all ready to go as well. Lesson 37 down here. Answers. So I'm going to be posting all that stuff shortly for you. So watch the video 7 more times if needed. LOL. And give those questions a good shot. You've got the homework solutions to help you through it. Remember, no.
The car going through the loop-de-loop.
Yep, absolutely. Let's do that. Let's watch some of this. Good choice. Good plan.
15 squared. Starting to cook my brain a bit now. 36 miles an hour. But you know what we haven't.
So see the pictures you got. You got the, you know, the centripetal force and all that stuff.
The total G force you will experience as you enter this loop.
See how he did see how you did plus G? That's exactly like I showed you. Like the G forces for the centripetal plus that G force you have to just even be sitting on the ground gives you the 6 Gs. So it's all the same stuff that I analyzed.
But at the end of the day, I don't know if that's going to count when I'm staring at the track from the accelerator.
But he's saying like, that's good. I know at least now he knows what speed to go in at, right? And then it's like, okay, let's try and do this.
To lessen the chances of Steve blacking out at the wheel, he needed to get used to pulling 6G. The only way
Nice.
to do that was in this. Here we go into the loop.
So they actually train pilots to force themselves to breathe. They almost like they make noises that they do. Like, they have to like force oxygen into their lungs because otherwise you forget to breathe. And so like there's training involved with pulling G forces and not passing out because blood gets pulled away from the centrifugal force pulls blood away from your head in that non-inertial reference frame. And so you black out. And so you flex your muscles to force the blood to stay, and you force yourself to breathe. And if you're in extreme situations, you actually have a suit that it puts pressure on all of your body, and it stops the blood from being able to pool down in your legs. But anyways, keep going. He for sure would have vomited, by the way.
The day fifth gear finds out if you really can drive a car around a 40-foot high loop-the-loop. If successful, stuntman Steve Trulia will set a new world record. If
He has to try and steer to stay on that white line. So you definitely have to have a contact force at the top.
The entry speed is therefore literally a matter of life or death. So Steve verified the car's speedo with GPS, 36, 37, and then checked again with a calibrated radar gun. 36 miles an hour had been calculated as the ideal entry speed. Slower than this, and he'd fall. Much faster, and the G-forces would knock him unconscious and exert a dangerous force on the ramp structure. The Toyota Aygo Steve had chosen for the stunt had been heavily modified to make it strong enough and hopefully safe enough should things go wrong. Here we go.
And then of course it's like commercial break. Just kidding. So remember, he'd be feeling the least amount of force from his seat up at the top. He'd be feeling like way more force here, and then it gradually goes back to normal force. And now you know why they call it normal force. Rock and roll. So pretty neat. I'm glad you asked to watch that. It definitely made sense to do that. All right. Cool. Done closing or stopping the recording. And